So let's get started with the industry session one. So the first talk is in charge of Thomas Müller from Simanto Research, a company in Germany and Spain. He's going to speak about active few-shot learning with FASL.
Thanks a lot. Thanks a lot. I feel like I've been set up and now sitting between people and coffee and like tired people that anyway. So yeah, this is a talk on active learning and few-shot learning. It's a joint work with Guillermo, Pérez-Torró, Angelo, Basile, and Marc, Franco-Salvador, done at the Simanto lab in Valencia. Yeah, so basically we'll just quickly introduce the terms that we've seen in the title. So we've already learned a lot about zero-shot and few-shot text classification, in particular in this keynote on Wednesday. So that will basically give you the right idea. It's to train text classifiers with no or little training data. And I think this was set up on Wednesday, in particular few-shot learning, where you have maybe 2 or 3 examples per label. For the purpose of this talk, we think it could also be a bit more. So maybe there's a human annotator and they are willing to actually annotate 100 instances, 200 instances, spend an hour, something like this. So this still enters into our definition of few-shot here. And then there's active learning, which I'm sure is something people are familiar with. It's basically this idea that you do iterative training, and you actually use the model to find informative instances that you then label, and then you basically get a better model. And the idea of doing this, or you do this with the hope that you can reduce the number of training instances for getting the same quality. Related to that, there are basically 3 research questions that we had. So the first one is, does active learning actually help if you do few-shot? And that's in particular because many, especially also corporate commercial solutions, they set quite a high bar on the seed set. So there's this idea that you start training an initial model on a seed set, and usually commercial solutions require like 1,000 examples, and then you start active learning. And we were thinking, what's if you don't want to annotate that much at all? So maybe you just want to annotate like these 200 instances in total. And especially this cold start scenario, which basically means when you start, you don't have any instances, seemed a bit under-researched. And then, of course, once you investigate that, you're wondering, of all the many methods that have been proposed, which one works actually best? And then there's a very special thing. So usually there's a human annotator, they want to get a good model, but they also only have limited time. So they want to understand when is a good time for me to stop. And usually if you do active learning, you have a seed set, so you probably also have a validation set, so you could just look at validation performance, and that gives you some idea. But if you do true few-shot learning, then you don't have any validation set. So how would you actually know when is a good time to stop? And this is why we came up with FASL, which is a weird acronym. Nobody really knows anymore how we came up with it, because the A is not in the right place, definitely. But here you go. Yeah, so it's a platform for active few-shot learning. So it combines active learning and few-shot learning. And it implements some prior work from the same group that we presented at ACL. That's basically a few-shot model. And it implements various active learning models, methods. And it has some way to estimate basically model convergence. So while you do iterations of active learning, it tries to tell you how your model is doing. And this is done without the validation set, which, as I said, you don't have if you do true few-shot learning. And the way this works is you can compute some signals on the unlabeled data that you do have. So, but we'll see more about this later. And then, of course, yeah, you want to do this as a platform, and there should be a UI, and this will actually allow non-technical experts to use this platform to build models fast. Yeah, what you see here is basically the standard diagram of active learning. So you start with an initial model, which is what is called create here. And in this work, the specific part is it's a zero-shot model, so you didn't train anything. Then you need, as I said, you need this part which is called evaluate, which basically tells you, should I continue annotating more data or can I stop? The actual active learning is this idea of requesting instances that are kind of informative. So this is where active learning comes in. Then you train a new model, which is where we use this label tuning that I'll explain in a bit. And then to actually decide, we use this prediction. So we have some kind of performance, or actually it's more convergence prediction of the model. And this basically allows you to at some point say, okay, this is good enough, I can stop now, and then you can deploy the model or run it on some data. Yeah, so basically this is like in this zero-shot, few-shot paradigm. We're using as the basis zero-shot models based on biencoders, which is very, very similar to what we've seen on Wednesday, where we had zero-shot models based on entailment. So the basic idea is you have some input text. Very proud of this. We always use this pizza is excellent, but I localized this for this event. And then you have your task, which consists of a set of labels. So here it's a sentiment task, and then each label needs to be expressed as a natural language sentence. And then what you do in the bioencoder world is just you have a bioencoder, which is probably some BERT model, just gives you a sentence embedding really, and then you can just compute a dot product, and that gives you your classification score. And as such, this is nothing new, right? People have done this for a long time using word2vec, using also sparse embedding models. But it really changed in recent years with the upcoming of models like BERT, and especially also the idea of fine-tuning them on paraphrase data and on these large NLI data sets that really boost the performance and really allow to get results that were unseen before. Yeah, and then once you have that, you also want this few-shot model. So we have one baseline here, which is the simple thing you can do is just you take the sentence embedding and you just train a logistic regression classifier on top. And then the other thing you can do is label tuning, which I'll explain now. So the basic idea is from the zero-shot example, that's how you start. So you embed your input text and you embed these label texts, and then you do this using a transformer model, and then you get these input embeddings and label embeddings. And for some input embeddings, you do have labels. So these are your few-shot examples. And then you can just basically multiply label embeddings and input embeddings, which gives you this matrix of classification scores, and then you can just put a cross entropy loss on top. And the important part for label tuning is that you only tune the label embedding. So you basically just freeze the input embeddings, which has two advantages really. One is you don't change the transformer model, which makes it very scalable, because later when you have your platform and you have many users, you don't need a new copy of your transformer for every user. So it's scalable, and it also makes training quite fast because you don't need to compute gradients through the transformer model all the time, because you can just pre-compute the input embeddings and then they're fixed. So you end up with a much easier optimization problem. And then yeah, at inference, it's pretty straightforward, right? It's like in the zero-shot case, you have your input text, you embed it using the same model as before, that wasn't changed. You get input embeddings, and then you have your tuned label embeddings, and you can just compute the dot product, and then this is your classification score. Yeah, so then regarding active learning, is like the missing bit. So there we just tried some of the most common methods. There's a bit range of a big part of active learning is uncertainty sampling, which basically means you compute probability distributions for all examples of some unlabeled set, and then you have some function of uncertainty that you use to rank the examples, and then you use the most uncertain examples to train your model. Instances of this are margin, least confidence, and entropy. So margin, for example, is just the difference between the probability of the label with the highest probability minus the probability of the label with the second highest probability, which if it's high means the model is very confident. If it's low, the model is very uncertain about this example. There's a different branch of active learning where you basically try to get instances with very diverse representations. And since we are using models that actually work on top of sentence embeddings, we already have a natural representation. So what you can basically do is you use clustering, and then you just draw examples from the different clusters. And the idea is that in your embedding space of your entire data set, you get basically good representations of areas with lots of examples with high density if you want. Yeah, there's some more specific methods that we also implemented and compared to, but that I don't really want to go into detail. We also tried combining uncertainty and diversity sampling, but basically it didn't work very well. So I'll also skip that. There's a lot of methods that we didn't implement. There's a lot of, for example, Bayesian methods, but they usually require an ensemble of models, and we didn't want to implement that into the platform because it makes everything more expensive to train. Yeah, now to the experiments that we did. So basically looked into a bunch of English, German, and Spanish data sets. There's Amazon reviews, which is like a very common product review data set with the typical 5-star rating. And then we had some text categorization data sets. So AG News and GNAT are news categorization tasks, and HeadQA, as the name suggests, it's actually a question answering data set. But every question also has a category. So we're just trying to predict the category from the question. All of these data sets happen to be very balanced. So they basically roughly have the same number of instances for each label, which I think is a property that is more frequent in academic data sets than actually in real data sets. So we also looked into what happens if you have unbalanced data, and we basically just enforced a Zipf distribution. So basically meaning that the second most frequent label has roughly only half the example as the most frequent label, and then it continues like this, basically with exponential decay. Here's some results. So basically, as you can see, we only compare some of the method that really worked best. You see here two models compared. So there's the logistic regression model, which is the dashed line. And then you see the label tuning model, that's the solid line. You see label tuning works a bit better on these generic data sets. And this is an average. And we're mostly interested in averages here because the idea is that later some user comes with their data and then they can't really tune anything. So you have to give them something that just works more or less on any kind of data set. So that's why we're mostly looking into averages. And what you can clearly see is that for logistic regression active learning, which is, for example, margin, the yellow line, it helps a bit over random, the green line, but not that much. And especially for label tuning, they're basically all the same line. So it doesn't really help. And this is also something that is more or less, I think, known in the active learning community, that active learning often doesn't work that well if you have very balanced data sets. If you go to unbalanced data sets, it gets a bit more interesting. So you can actually see here that there is a much bigger difference between active learning, like margin, the yellow lines, and random selection, the green lines. And yeah, the difference is, for example, so big that now logistic regression with active learning is actually better than label tuning without. But otherwise, it's the same picture. Margin is the best working active learning method, and label tuning works a bit better than logistic regression, especially in the early stages. Now we come to this last part, which is really this question: how does the user know when to stop? I said it before, we don't have a validation set. So we can't just do held out validation. And then we had this idea, can we just predict based on some unlabeled data how the model convergence looks like? And what we thought is a good approximation of model convergence is basically just the F1 score normalized to 1. So here you basically see a training curve over time as you add more and more examples, and basically the performance goes up and then it converges at some point, more or less. And we normalized it because we don't expect that we can actually predict you're going to get 60 or 70 or 80 F1 score without knowing the task, without knowing any of the data. And then how do we do this? Well, it's just a simple random forest regressor that basically has some signals from the current time step and some signals from the previous time step, and then it tries to predict. What is predicted is, as I said, normalized F1. And then we use multiple features to do this. So one thing you could do is just use cross-validation performance, right? So because over time you gather some labeled instances, so you could just evaluate on them using cross-validation. But as you can see on the right in this blue curve, I guess it's a bit small maybe, cross-validation doesn't really work if you do active learning because you always select hard examples. So your labeled training data is not a good representation of what you actually would have as a test set. What you can do instead that works much better is compute all kinds of signals that try to estimate how uncertain is my model about the unlabeled data that I have and how does that change over time. So one thing is all the active learning methods that we use to select instances, they give us some uncertainty, some notion of uncertainty, and we can just average this over the training set, and that gives us some number. And over time, we expect that the uncertainty on the unlabeled data goes down. So if we basically put a minus in front and we have a curve that goes up, so it's relatively similar to the convergence. Another thing that you can do is, for example, just look at how did examples change from one model iteration to the next. For example, just looking how often did a label flip, did a label change? This is what we call update rate here. But you can also, for example, do something like Kullback-Leibniz divergence and just compute what is the difference in the probability distributions on average. Here you basically see how this works. So we see this for margin learning, like active learning on the left, and then the random baseline on the right. What you can see in the upper plot is averaged over multiple random runs, how the F1 performance develops. And the shaded blue area is the classification error that our model does. And as you would expect, it's basically a bit off, or like quite off in the beginning, and then at some point it gets an idea of how this is actually going to go over time. And in the lower plots, you see these different metrics, and you see here, for example, that there's some like negative update rate that correspond quite well to this normalized F1 curve. And again, you see, for example, cross-validation, which is this blue line, is kind of okay if you do random selection, but if you do active learning, it's not a good thing to use. But as a signal, it's still something that you can use in the model. This is just one attempt to put a number to if this actually helps. But I just want to say, it's like the most interesting thing for me is to give the user a curve, and then they can actually look and try to see it. But just to see if this works as a stopping criterion. So we just thought, okay, let's assume the user wants to stop when they reach roughly 95% of the quality that they could ever get on this data. So it's just their quality goal. And it turns out that on average, over all the data sets and multiple random runs, this is like roughly the case after selecting 288 instances. So this is kind of the baseline where you say, okay, I'm just going to train for this fixed number of instances. So now instead, you can use our model and you can say, okay, I'm going to stop when the model tells me that the predicted estimated performance is 95%. And what you see here is, yeah, when you do that, you actually get a bit closer to this 95% goal. So it's actually doing a bit better, but you also especially get closer to this goal of getting this exact performance. And on average, you have like slightly less instances annotated. But that's basically, yeah, as I was saying, this demonstrates that the method works, but I think the most important part is not to have a heuristic that just tells you stop now, but it's actually this curve that a user can look at. Yeah, so to conclude, so we basically looked into active learning for few-shot learning. We built this platform called FASL. Looking into active learning, we found margin sampling works quite well, but only for these unbalanced tasks where you have like some unbalance in your label distribution. We also looked into if you can predict performance or rather convergence of the model, and we found this you can do this to some extent, and basically we built this platform FASL that integrates these ideas into a platform. Don't know how, yeah, I think this is basically fine. Yeah, this is basically what I wanted to say. Thanks a lot. Happy to take questions.
Thank you very much, Thomas. Does anybody have any question?
Hi, thank you very much for the talk. I have a question about the slide in which you showed this scheme with the label tuning and the model you used, because you said that you use similarity and cross entropy loss, or which is
This slide?
Yes, this one. You said label tuning, similarity, and the other loss. Which...
Yeah, it's a cross entropy loss. So it's basically cross entropy loss on top of your similarity metrics, right? It's just the metrics of all the dot products.
Okay,
and
okay.
Yeah.
And then I suppose, for example, for a positive example, the similarity between the input test and the label test should be reduced, and the similarity between input text and negative label test should be increased. Or
you could do that for a binary task, but in general, you can just assume you have a matrix. Here are all your examples, and here you have the columns are your labels, and then you have a score, and then it's exactly like a logit in a normal neural network, and then you put a softmax on top and do a gradient update, and that's exactly what we do. And the only difference is really that we freeze the network, so you only tune the label embeddings and you leave the model intact. But otherwise, and there's also it's not here, but you also want to have a regularizer that makes sure that you don't move too far from the label embeddings, because you have very few training examples. Otherwise, it would be very similar to just training the model. Yeah.
Interesting. And the last question is about the problem with imbalance. Have you considered to upsampling the low represented samples using different label text? For example, a positive sentiment could be expressed in different ways. So maybe if you create, different label tests for the same feeling, you can try to create new samples for the low represented classes. Or
so you mean, so I guess at the time, like for your unlabeled data, you can't do any upsampling, right? Because you don't know what the class is. You can do it after you selected labeled instances. You can do upsampling. We didn't try this, but it could improve quality a bit, right? But potentially.
Okay. So thank you.
Thank you, Thomas.
There's one more question.
One more question, sorry.
I just wanted to ask about the label embeddings. How did you obtain them? Because I can imagine that the input embeddings can be from get from the transformer, but for the label embeddings, it's that you need to define the label by text, or how?
Yeah, so it's exactly that. So you need to write a text that describes the label. So for example, for sentiment, you can try something like this. This text expresses a positive sentiment.
So it's not possible if I don't have a specific word for that label. For example, I have something like movies and music together, like this one.
Yeah, I mean, you have to phrase it into natural language. If that's hard, it's a bit tricky. So for example, if you do hate speech classification, you cannot just say, it's something we found, you cannot just say this is about hate speech, because you need to define what hate speech actually is. So you have to say this is hostile, insulting, toxic in some way, or attacks ethnicity or something like this. And then sometimes it can be really hard if you have a class like other. Yeah. Then you might have trouble defining a good way to say it's not the other stuff. Yeah.
Okay, thank you.
Any other question? No, thank you very much, Thomas. So next talk is going to be online. Fabio Tavares from the CDR Research Institute in Brazil is going to speak about, give me a second, automated triaging in a global software development environment and industry experience. Thank you for this. Fabio, are you there?
Yes.
Okay, can you try to share your screen?
Can you hear me?
Yes, we can hear you.
Yes. I will share the screen.
Okay, let's see. Okay, we can see also your screen. So go ahead.
Okay. Thank you. Start video. Okay, hi everyone. Good morning. So let's introduce myself. I'm Fabian Tavares from CIDIA, an Institute of Science and Technology in Manaus City, Brazil. First, I'm not the author of the paper, but I represent them. As you can see on the screen, our topic today is automated bug triaging in a global software development environment and industry experience from the company CIDIA. And I divide my presentation into 4 parts to describe the case. First, we'll focus on the problem, then on the approach, after that, the experiment, and finally discuss some results about this. Okay, let's start with motivation. Large companies maintain software development distributed across the several countries. And these advantages come up with the cost of the management, while control project development is a challenge. Coordinated the distributed effort to solve bugs is even challenging too. Identify the best team to analyze and fix a bug report is a non-trivial task for a large application and system. They are often developed by different groups and different life cycle and use on a complex set of technology. Recently, literature has presented a number of the initiator project based on machine learning techniques that aim to automate bug triaging for a large project and use the word embed techniques. Now, then I can show our goal. Our paper, we analyzed the performance of the shelf fast test classifier in the problem of bug triaging, and we compared the performance with LC25 method is a kind of BM25 implementation, which show promising result previously. Now let's define the problem. The bug triage problem is defined as an automated classification method that takes as input historical data and set of historic technical groups and a new bug. And then we'll return an ordered list of technical groups for a new bug. And then the rank position of the level of the fix the bug or to direction to solve the bug. On the screen, you can see a graphical description of the bug triaging problem. The rank implementation received the new bug and the return the sorted list of the groups. This is supported by the classifier, the history. Here you can see related works with different approaches and techniques. And in the paper, we analyze and discuss the best strategy to improve a new approach. For example, use the word embed combining with different supervised classifier types, and then we choose the best one as a baseline. The related work use different approach to classify and different approach to text representation. Now let's take the proposed approach. Our approach is supported by off-the-shelf methods or competitive available methods. The goal is to define how well a simple architecture can compete with our previously defined state-of-art method. And now we can define the important part of this approach. So the text representation, a bug report is composed of both textual and categorical attributes. Here you can see the textual title, description, step to reproduce, and categorical model name, model detail. We composed all attributes in a single test to allow the model to learn a text embed that represent the bug as a simple, but the side effect of the approach presents some drawback, but because the categorical attributes have potential to semantic mismatching. When artificial added the test attribute, we discussed in the experiment. Next step is represent the bug report to the classifier. We use the fast test to represent a bug report. The fast test encode the single test as a vector, and we use the auto-tune to feature from the model to automatic optimization the high parameters that better fits our data set. In the test attributes, like title, description, test to reproduce, are preprocessed using standard techniques, tokenization, stand, stop, reward, remove. The last part of the approach is define the classifier. The classifier is similar to the present by Jolie. The classified training on a linear regression with stochastic gradient descendant or normalize the text vector, which is generated from the mean of the vector dimension that compose the test. Finally, it implements a hierarchical softmax to identify the class, which take into consideration the hierarchy between the technical groups in the institution. Now the experiment, we test our approach using a real world data set from a global leader in mobile sector. The data set contain more than 400,000 bugs reported, collected in 6 months. We use a rolled out strategy to split and the data set in the train test, 9% the train, 10% test. The split take into account both the distribution of the technical groups and the chronological order, the bugs. The experiment were performed with the settings. As I mentioned before, we compared the performance with LC25 approach method is a kind of extend of the BM25 implementation. We showed the promised result privilege as a information retrieval approach. LC25 is implemented using linear combination of the report attributes 8 by 80 degrees importance. The similarity of the textual features are measured using the extension of BM25. Where similar, the categorical attributes used to simple comparison. And so this brings the result. We can see on the screen the difference between the result of two models. T-test has been used to determine the difference between the result of two models. Okay, some points from the results when only textual features are used, the difference between the fast test and LC25 is significant. Another point, when both textual and categorical features were used when composed in a single vector, the fast test based model outperforms the LC25 model. But when considering high ranks, the LC25 models outperform the fast test and top 10, top 12. And I'd like to highlight this is the best result. Our approach reduced the experiment time by 90%. Our experiment showed that selecting the data set composed of more recent bugs report increased the performance, whose distinct this result made the attribute data set proper. Features work, our strategies can be expanded and improved, and with the follow feature work, investigated the other strategy to explore, use the categorical attribute, use combine the BERT textual representation, and analyze the use of the hybrid models to take into account source code feature to extract the source code feature from the bug report. So to finish, I'd like to sum up the main points. The experiment indicate the proposed approach can deliver better performance, improve the runtime, the experiment, and use the real world data set, because a lot of the related work use open source, small data set. In this paper, we presented analysis of 2 of the shelled methods for the problem of bug triage in a real world center, with a targeted sets of 100 of technical groups and more than 400,000 bugs reports. And deliver the better performance. Is this? Thank you so much.
Thank you, Fabiano, for the talk. Does anybody have any questions? No questions?
Yeah, I was wondering if you actually deployed this, and then this seems like this ideal application for machine learning, because you make a decision and later you learn if this decision was correct. If it wasn't correct, probably someone changes the bug assignment, and then you can retrain the model at some point and learn from previous mistakes. I was wondering if you looked into that.
Okay, I'm not afraid to detail this point. I'm not an author, but you can send me an email to this. But I'm afraid to say the detail about this. Okay.
Okay, Fabiano, we will do that. We will send, if there are more questions, we will send them via email to the authors of the paper. Thank you for presenting on their behalf.
Thank you. Thank you.
So we are going to move the next talk to after the coffee break, because we don't have time now. And later there is another talk which is not going to present. So we will have more time. If anybody is not going to attend the lunch, please confirm to Berta, because she has to speak with the restaurant. So if there are no more questions, we can go for the coffee break and see you later. Thanks. Okay, welcome back to this industry session 1. We still have one pendant talk by Alexander Banshee. Is it well pronounced? Okay. And Felipe Kunchik. Okay, they are going to speak about the slot filling for extracting, reskilling and upskilling options from the web. They come from the University of Applied Science of the Grimsons in Switzerland and the Web Lizard technology from Austria, right? Okay. So the floor is yours. Let's see, you can minimize this.
So I hope you all enjoyed your coffee. Now you are refreshed and able to listen to us for like a whole hour. PDF. Down. The second last. No, second last is one P3. Yeah.
Spanish.
Yeah. Now it's perfect. Perfect. So thank you for joining us. We're talking about a research project or applied research project that we did at our university. I will just go a bit about who we are, because I don't know everybody knows where the University of Applied Sciences of the Christians is. Then I will talk about the career coach project that we did this paper about, what we do there, the system architecture that we used in this project, and we will introduce the career coach corpus, which is like 169 documents in German language, where 75 are fully annotated and the other ones at least have segments. We talk about our systems and the results that we achieved, and finish with the conclusions. So short view on the friendly faces that we are. We're around 6 people, more or less. Those are the main people. Albert Weichselbraun is basically our superior that is like the main person of interest there in this NLP community in the Christians. We are located here in Chur. I don't know if you know much about Switzerland, but there are like the biggest cities around one axis, and Chur is like very peripheral. So we have like 100 kilometers to Zurich, and this is the closest city that we are. So everything in our direct surroundings is directly affected with us. It's an old town, and it's the oldest city in Switzerland at all. And we have lots and lots of beautiful mountains if you want to visit. Some numbers about our university. We have 2,000 students in the bachelor's and master's degree, so pretty small, around 200 people teaching and doing research at our university. The NLP team that we are most probably does only applied research projects, so we also got some grants from the Swiss National Fund, which is like more advanced research fund. I think you know it. We have cooperations with the Swiss National Supercomputing Center in Lugano. For example, if the resources that we have in our university are not enough to train a model, so we can just move it to Lugano and have the bits dined with its one of the top 20 computers in the world, I don't know, to do the calculations. And we also have like diverse partnerships with all kinds of branches. I just listed here the 3 most prominent ones that we did the research in the last 8 years. Our main funding opportunity is InnoSwiss, which is like a applied research project transfer method to get our innovations or the academic innovations into industry. A project normally has like 18 to 24 months and is like 500 to 1 million francs of total budget, where 50% is fully funded by the federal agency, and the other 50% are in-kind powers that the industry provides to the project. Exactly. In this context of the InnoSwiss project, the Career Coach project is one of those. We try to mitigate the problem that the educational landscape in Switzerland is quite diverse. You have 488 educational providers that all have different layouts of their websites, and we try, and also different content on their websites about their educational programs, and we try to extract all those information that we can find about the educational programs and structurize it in an intelligent way, so that we can after that do build a recommender system on top of it to get people to have people informed about their possibilities for reorientation and upskillings. So the project outline basically is get all the data that is available, do information process on all those information extraction on all those data that we can grab, and build a recommender system in the end. Slot filling, I don't know if you know it, we define it as the task of extracting knowledge that corresponds to a certain parameter. In our case, in the Career Coach project, we had those 7 slots As you can see in this table, there may be more or less cardinality, so more or less annotations that relate to this one slot. This table in the middle, or this list in the middle, basically are the types of entities that we try to extract and put into those slots. For an example, this is sadly in German, but I think you can get it if I explain it to you. You have the red box, which is like the page segment that we extracted containing all the course contents. On the right top, you would have a tab button where you can switch to the prerequisites of this course. And the blue ones below are basically annotations that we extract. If we can map them, then we map them to the existing ontology. If we can't map them, then they are in another project. So we also differentiate between known and unknown entities. This basically is the system overview that we created in our in this project. We see web crawling as basically a solved problem, so we don't we will not further go into details with the web crawling because it just works. Alexander then will talk about the page segmentation, the entity linking, and named entity recognition, so for known and unknown entities, and then about the results in the slot filling task. And therefore,
yeah, let's jump into the page segmentation. So the first step we did was after getting the crawled web page, we tried to segment this web page into specific segments. Most of the part was really a title followed by the content itself. And it follows this structure you can see in this image. So first title, then segment one, or maybe even a second one, and followed by the next title and its segment. We did this with a heuristic approach. So most of the time it was based on HTML tags, how we derived our segments. And in several cases, we just needed to also analyze what's within the text. So maybe there was a clause or some additional meta information we could use to derive those segments. Based on those segments, we followed with the entity extraction. In the first step, we used existing entity linking web service to get the entities. And this linking service is based on a graph, or is a graph-based method who recognizes and links the entities of our ontology, of the ontology of our partner, which you can see here on the left. Like Philip mentioned already, we did see some unknown entities, and therefore we used the deep learning approach, which was built on the Distelbert German case language model. This model, we adapted it with some silver documents of our entity linking component. So we had quite a large silver standard, which we used to adapt this language model, and finally fine-tuned it with some with those 75 mentioned gold standard documents, which were like the top of our model. Here you can see a broad overview about our configuration values. Like I mentioned, it was a Distelbert model, exactly. So next step, I give you a broad overview about our corpus. It was divided in two parts. So the first part, or the first partition, was really just identifying the segments. So we had 169 goals documents. Everything was in German for the start, and those were derived, or we discussed it with our partner to have like the most important providers to get a broad overview about the entire domain. Since there were all as well providers which just had like few examples we can use, and this would have resulted in a model we couldn't use that well. So we decided therefore for the high priority education providers, which got a bigger portion of our sampling in the gold documents. The second part, or the P2 here, is the mentioned gold documents which were fully annotated. So those documents include as well the entities, which we can see now in the next slide. So this is our corpus in numbers. So like I mentioned, the P1, which held more documents, had in total 575 page segments, which we annotated, while the other corpus P2 with the entities had around 3,291 entities with it. The corpus or the gold document itself looked like this. We had the HTML, we had the text extracted with Inscriptis, and we had those two parts like the page segments and the entities, which were basically, a segment was just the text we annotated with the start and end position and its content time. So meaning if it's just text or if it contains maybe also a list or a table with it. The annotation was as well the surface form, so meaning the text with start and end position, and several keys, so like the key we derived from our entity linking service, and some additional links if they were present from a common open source knowledge graphs like Wikipedia and DBpedia, as well as ESCO. So now finally we arrive at the task we perform at the project, as well with the results we achieved in those tasks. So the first task was to identify those annotated page segments from the web page. And the second task consisted of classifying those segments into those outlined slots we showed earlier. The third task was entity recognition, so identifying the entities in those page segments. And the fourth step, classify those entities as well for those given entity types we showed in the slot filling slide. Exactly. The fifth task was then entity linking. So can we, how good was the mapping with our knowledge graph? And finally, T6 concludes all of the all of the previous tasks, so T1 to T5, which finally presents how good was our pipeline from start to end. Here you can see a broad view of our results. For the first two tasks, we achieved a F1 score of a little bit more than 0.8. The scores are quite similar or exactly the same, which indicates that already the page segment recognition tasks already provided the exact same results, or as we wanted to have in the classification. And this we could achieve through like words which we extracted from the title, so which said, okay, this is a course content, and that was for us the information. Okay, the following part might be the segment for course content. T3 and T4 have a higher value, or especially higher value in the precision, and yeah, we can also say this was optimized for precision, since the new entities were undergoes the manual validation process. Whereas the next task, T5, was optimized for recall, since we already had the information of the given page segments, which helps to classify those extracted entities. Here we have a difference between strict and relaxed matching. So strict would mean we needed to have the exact matching of the entity itself, whereas the relaxed setting allowed to have an overlapping entity recognition or just a part of the entity. So therefore, the values are here slightly higher than the strict setting. The last part, T6, indicates it's around, or our F1 is a little above 0.5. And we clearly see here that it's not suitable for fully automation, but for our partner, it's quite a advantage of time limitation. So the process could be speed up, which was a huge improvement for the daily work of our partner. So to conclude, like I mentioned, the results of the full pipeline were not as perfect as we probably wanted to have them in first place, but they led to a big speed up of the manual work of our project partner. What you also can conclude that, like here mentioned in the overview, that every task is dependent on the next task. So if we achieve 0.8 in the first task, this is like the new baseline for the T3 task. And this is error prone. So if you have a baseline of 0.8, we can't get to a higher value after this task. And the last conclusion for us was the data pipelines and continuous integration for our components are quite useful, since we can then just deploy the components by clicking and having instant feedback if it's was deployed or how good our results were. In our future work, we will focus our time in optimizing those presented components, and we also will train our components with even more data in order to obtain an even better ontology coverage. So meaning recognizing even more entities, which will then be added to our partners' ontology, etc. At the end, I want to say grazie fich per l'attenzione. We translated in all of the 4 languages in German, and we are open for your questions. Thank you very much.
Thank you very much. Does anybody have any question? Who is managing the mic? Berta is not here. Nobody is managing the mic.
I think at the camera.
No.
At the chair, at the camera.
Oh.
Test.
Yeah.
Thank you. Thank you for the interesting talk. The final conclusions said that what's going on is, since you divide this task into so many subtasks, is that you're getting a lot of error propagation, right? So the last task is what you're most interested in, but since some accuracies earlier on are a bit lower than you would like, that shows in the final result. And I think it's super interesting to think of HTML, which is your raw data, as kind of natural language, which it isn't, because it's very structured and all that. But wouldn't you, for this final task, then maybe want to work on it like a joint learning problem, that you just input the raw HTML files and try to find in some way the structure as one task?
Our pipeline input is not HTML, but the text that is contained in the HTML. This Inscriptis component is made to strip all the HTML away, but at the same time keeping the layout of the content itself.
Okay, then I'll rephrase my question. Would you like to use raw HTML? Because I feel like the H tags, for example, the H1 tags, they work probably most of the time for dividing the sections and whatnot. That's already kind of a heuristic you use in the beginning.
Yeah.
But maybe it could learn itself how these websites section text?
So we have lots of experience with web crawling and web intelligence and stuff like this. And what we experienced in those examples is that you can easily create like a parser for a single website. But if you want to scale it on like every website that is out there, you cannot just use the HTML, because every company, every website just uses the HTML differently. So for example, if you have a look at tables, there are still lots and lots of use cases that just use tables to lay out the whole website, which just breaks most of the time everything that you can imagine. So we want to strip it down from the HTML to the text to get rid of all those problems that we would have with the HTML, except if you have like one single source that you want to observe.
Okay, thank you.
Question? Thanks for the talk. I was wondering a bit about the precision number for slot filling. So intuitively, I would have expected maybe higher precision and lower recall. So maybe you can comment a bit on what kind of errors you see on the slot filling. And then related to what you said, that later you pass that on to the client, and then I assume they manually correct the frames that you produce. And so if they have a preference on, if you trade off precision recall, like do they have a preference when they manually fix this, or is like now it's relatively balanced? Is that what's working best in this situation?
So to your first question with the slot filling, I think this is exactly that example that we that shows that error aggregates over time. So if you have, for example, those named entities, and those named entities are in different types. So we have the type of the entity. Just going back to this slide, we have the slots on the left, which is like 7 different ones, and we have the entity types in the middle. And one entity type could be in different entity types. We try to do it like automatically to get it in the first in the correct slot the first time. But as you can see, there are different types of entities that we try to get into them, or that we try to get into different slots, and therefore it just diverses a bit. Yeah. And to the second question, so this is applied research. So we always have very intensive talks with our clients, and with the client we decide what is better for their business case. For example, if you have I don't know, we had a problem where we wanted to do to monitor media criticism, and it was like in the social sciences area, and those people did not want to look at false positives all the time. So we tried to train it completely on precision, because they were getting mad if they would see some examples that they that doesn't contain any media criticism. And at the same time, they're also getting mad if they do not find any document in like the corpora that we created from all this. So yeah, it's always a trade-off, and I think we always try to like get it together with the industrial partner to have it like that it fits their workflow.
More questions? No? Thank you very much. Next talk is about zero and few shot learning for author profiling, and it's going to be given by Mara Chinea Rios from Simanto Research.
Hello, everybody. My name is Mara. I come from Simanto AI Spain. And today I will present this work with my colleagues from Simanto, Thomas, Gretel, Francisco, Rangel, and Marc Franco. And the title for this paper is Zero and Feature Learning for Auto Profiling. So background of this is what is auto-profiling, or what is the task of auto-profiling. So auto-profiling aims to identify some characteristics or traits of the user by his sociality activity. We can determine or found different traits like age, gender, is the user is a hater or no, many others. The thing is that the data annotation for auto-profiling is a very challenging task. How it shows during this data annotation is hard for a lot of stuff, but in specific for auto-profiling, they have some very extra economic costs, temporal time, and the experience that we need for the annotation for this specific task is very hard. For this reason, in this paper, we propose the use of zero and future test classification. I don't want to repeat all the times that the same that we saw during this conference, but basically for the idea for zero future is train and a text classifier with a liter label data. In the extreme case, we have zero shot, well, we don't have labeling data. Basically, we want to, or in this paper, we use the few and zero shot in the entailment approach. Oops, sorry. This paper have different contributions. The first contribution that we want to include here is that we study auto-profiling from low resource viewpoints. And also we compare different entailment models in this paper. Also, we studied to identify 6 different auto-profiling tasks in 2 different languages, English and Spanish. We analyzed the effect of the entailment hypothesis, and also we analyze the size of the few short user samples. And finally, we present an author instance selection method. That the idea in this method is to select or identify which part of the user test is the most representative for the task. So as a very quick introductions about entailment approach for zero and future test classification, the entailment approach consists of using the input test of the classification problem as the premises, and an hypothesis in the textual, and the textual form is then defined for each label, and the model applies to each text hypothesis pair, and the label with the higher entailment probability is chosen as the predicted class. Okay, we can use this entailment approach in the future scenario, how we saw in the previous class. The neural model most used for entailment approach is the cross attentions. How Thomas explained, the idea in cross attention take the both input, the premises and hypothesis, and they're encoded jointly. But with cross attention, we have some problems, or maybe some difficult to deploy and escalate. Why? Because the inference is low, especially for large label tests. The fine-tuning is expensive, and the underlying model are huge. Fine-tuning will change all the weights. For this reason, some authors, in this case, some colleagues from Simanto, propose the use of bioencoders or Siamese networks for this entailment approach. So basically, the Siamese networks encode the premises and the hypothesis into the high-dimensional vector space and use a similarity function to find the hypothesis that best matched with the input test. So basically, with biencoders, we can able to get results comparable to cross attention, but reduce the temporary efficiency. What about the auto-profiling? Well, in this type of task, auto-profiling represents each author label as a collection of tests. So basically, we can get the user label, and see all the probabilities of classification of all these texts. Follow this equation, where C is the total number of cases, and we have an list of tests of the specific author. The thing is that we saw that in many cases, the label text for the text are of an author are random, and in many cases don't represent the real label for the authors. Because so follow this idea, we can find some noise or some misleading instances. For this reason, we propose an instance selection method that is a very simple method. So basically, we want to select the success of this list of text more close to the center for all the cluster, for the cluster for all the text for the users. We obtain this cluster, apply an agglomerative clustering method. For the experiment, how I say, we testing our idea in many different auto-profiling tasks, especially 5 different auto-profiling tasks. The first group of these tasks is a demographic task that include gender identification, age identification. Then we have hate speech, bot detections, fake news, and finally the depression level. The first group of tasks, the 5 tasks come from the PAN competition share task, and the last one was a share task for IRIX the last year. Some details about the experimental setup. All the models that we used in our experiment are pre-trained model hosting in Hugging Face. In the case of cross attentions, we use an bar ledge model for the English and XLM Roberta for model for Spanish. And in the case of bioencoder or side-mixed networks, we use a paraphrase multilingual MPNet base. It's a model, it's a sentence transformer model. All this model has been training on NLI dataset like SNLI, MLI, and others. The first things that we discuss or we analyze in our experiment is the hypothesis could be affect the results of the zero shot results in this case. We saw that yes, the hypothesis could be change our results. In totally, we testing 68 different hypotheses. And we include the identity hypothesis, which represent the label used is the raw string label. And here in this table, I shows the best hypothesis for each language and task. We can show that the label, the hypotheses are very close to the task. And also, you want to see complete this with result of all hypothesis explorer and all the experiment. We have all these available in our repo. About the experiment, we're running a lot of experiment comparing different things like the different entailment models, cross attention by encoder. The other experiment that we're running was the total comparing with training the entailment model with respect to the future learning. Or we also explore what happened, or is the instance selection method is effectiveness or not. For this reason, we compare with the random instance selection. But today, I cannot present here all these experiments. So for this reason, we only chose 2 results for two tasks in English. This is the validation results. Basically, here we want to show what happened is we make few shot or training with all the available data. We chose results in terms of user per class S1. The horizontal lines are the entertainment models training with all the available data. For example, hate speech is 100 user per class. And the other two lines is the training, the future models. Instant to see here is, for example, in the case of bots, cross-attention on science network have very similar behavior, but in hate speech, cross-attention, when we train with all the available data, have better behavior. But when we make few shot, science networks works better. It's amazing to see how we can able to get with a small number of users similar or better result that train all the model with all available data. And in the case of both, we don't able to get better result than the training with all, but the number of users is very small with respect to the total. Some highlights that we want to include here is that in our experiment, we saw that the author instance selection get competitive results in all cases, and thus reduce the training time and cost. This has like the capability to select the most relevant training instances. In English results, science network or by encoders outperform cross-attention in 4 tasks, and in the Spanish, science networks have performed in 3 tasks. So basically, we saw the science network or by encoder as most stable across tasks and language. Oops, sorry. Yeah. Okay, some test results. In our paper, we compare our results or our idea with different approach or state of the art or baseline models. But again, here, I only want to choose one of these baseline, so that we call winner. This is the best position, the best result that the best results that have for this competition is the model that ranking first for this difference competition that we found in the overview. And we compare the results with 0 and few shot. Here in the case of English, it's very interesting to see what happened in hate speech and depression. 0 shot is able to get much better or very similar result with respect to few shot. So this is amazing because this shows that in this type of task, this type of approach could be great if we don't have any data set. And with respect to few shot, makes a very good work because we can see that this winner approach was training with all the available data that they have in this moment, and in some cases they use other resources for this, and at the same time they create this model for this specific task. For us, we don't create anything for the specific. We are trying to base the most general with our idea for all these tasks. What happened in the case of Spanish? Well, the results are very similar or have the same behavior that we have in English. In this case, few shots have very good work. We don't use all the available data, but we can able to get very similar or very comparable results with their winner. So this is amazing. As the conclusion in this paper, we study auto profiling for low resources perspective with a little or not training data. We address tasks for using 0 and few shot test classification. We studied the identification of 6 different auto profiling tasks into language. We analyzed the effect of the entailment hypothesis that we saw that this affect the result for 0 shot or at the same time few shot. We analyze the size, or is the size of the future training sample affect the system performance. We compare two different entailments models, cross attention and bioencoder. And finally, compare work results with the state-of-the-art. We see that we can reach 80% of the state-of-the-art accuracy using less than the 50% of the training data on average. So this is amazing, because we can able to reduce the number of data that we need. Thank you so much. This is our.
Thank you, Mara, very much. Any question? Hello, Mike.
I have two questions. The first question is regarding the clustering process that you mentioned. So the clustering that was done, was it with respect to the tweets of the user, or whatever information you are taking of the user, or clustering of the users in general?
No, the cluster was made based of the test for each specific user. So basically we select for each user some instances and go for all the users, no in general. Yeah.
Okay, so my next question is with respect to the usage of paraphrase sentence transformers. So in general, the tweet data would be not well formed, but the data set on which the sentence transformer, the paraphrase sentence transformers are trained are very well formed and grammatic. Do you think those would eventually affect the performance of the system?
Well, basically, I don't know. We follow this idea, but we don't think and you say right now about about this problem. Maybe we can make some experiment to see about
Okay.
this.
Yeah, thank you.
Any more questions? No? So thank you very much again.
Thank you.
So next speech is going to be online. Angelo, also from Simanto Research, is going to speak about unsupervised ranking and aggregation of label descriptions for zero-shot classifiers. Let's see if I can.
Hello.
Angelo, are you there?
Yes, can you hear me?
Yes, we can hear you. Try to share your slides.
Yes. Can you see my screen?
Yes, we can see your screen. We can hear you, so the floor is yours.
Thank you, Kiko. Hi, everyone. Welcome to this talk. I'm Angelo, and today I'm going to present joint work that I did with Marc, was supervised by Paulo from UPV, was part of my industrial PhD in collaboration between Simanto and UPV. The title of this work is Unsupervised Ranking and Aggregation of Label Descriptions for Zero-Shot Classification. So I'll briefly introduce the background of zero-shot classification with label descriptions, even though I think you've heard enough of it today. And then I'll jump to the research questions and the experiments. Yeah, so traditionally in fully supervised learning setup, we have some input text that we want to classify. We have some model parameters theta, and we want to know the probability of seeing some label. For instance, we could ask the model, what's the probability of seeing label 0 given the text, I missed my flight, where label 0 stands for, say, class negative, and then we have some label 1 that stands for class positive. And note that we encode the label in this case as a discrete category that's completely meaningless. We are not going to specify or to tell the model anything about the label itself. In zero-shot learning with pre-trained language models, what we usually do, we still have our input text, we have our model, but in this case, the label is encoded using a natural language. So the problem becomes, what's the probability of seeing some text that describes the label given some input text to be classified? Let me make an example to make this a bit more clear. Here's our input text. And then we start writing a label description. Let's say for class sad, this person feels sad. And then we do the same for describing another class. Let's say this person feels happy for class joy. And what we do, we embed both the input text and the labels in the same semantic space using sentence transformers. And at this point, we can start measuring the distance between these different texts. Let's say D1, D2, we use a symmetric score function for efficiency reasons, and dot product in this case. And then at this point, with some simple arithmetic, we have all the ingredients that we need to turn a semantic similarity model into a zero-shot classifier. So we can say that if D1 is less than D2, then we classify the input text as being part of class set. The reason why we focus on this type of models is that they are really interesting from an industrial perspective, since they allow for fast inference for reasons that probably Thomas and Marc already described. And they can be as good as cross-attention models with some tricks. But let's take another look at this. So some person, the end user of this system, had to manually write this label descriptions. Now imagine that the user would have written something like, this person feels unhappy for the class said. It can be the case that this representation would be further away from the input text, right? In this case, would result probably in a incorrect classification if we didn't have D1, right? This is an hypothetical example, so let's look at a real one. We want to build a sentiment analysis model using the IMDb movie review dataset, so a zero-shot model, using our sentence transformer model, a pre-trained model. And we start by writing the label descriptions, final review set for class negative and final review awesome for class positive. This is movie review data set, so we could write something like this. And then we write another set of label descriptions where we use the word bad instead of sad and great instead of awesome. In principle, these are like both reasonable label descriptions. We are in a zero-shot setup, so we don't know which one is best. So in this case, we have the labels since we have a label dataset. And when we do the evaluation, we see that there is a gap of 6 points between these two label descriptions. So given the same input text and the same model, we are going to have different probability of seeing very similar label description that will result in high difference in terms of accuracy. So based on this assumption, what we ask here is how do we find a label description Y that it can maximize the performance of our zero-shot model on some input text. And we want to do this without having any access to label data since we are in a zero-shot setup. Okay, if you think about it, this is the same problem that we have when we commission some human intelligence tasks, say on Mechanical Turk. We want to annotate some data, so we have this text, I missed my flight. And then we have some crowd workers, and they will give us some labels for the same text. Some will say negative, some will say positive. And we don't know which one is the correct label. And what we suggest in this paper is to view zero-shot models with different label descriptions as crowd workers. And if we follow this analogy, basically we can then tap into the literature of crowd annotations modeling. And if we do that, first thing we get is majority voting and inter-annotator agreement metrics as baselines for label aggregation and for worker model or human annotator scoring in this case. And then if we look a bit more in this literature, we can find what is considered to be the state of the art, which is to use item response theory as better alternatives for these baselines. In this case, we suggest to use Bayesian generative item response theory models. These models have some parameter theta that can model the generative process of the annotation, things like average annotator accuracy or class prevalence. And then given these parameters can generate some labels. And then thanks to Bayesian inference, we can reverse this process. So we want to infer these parameters given some observed labels. So this is what we would have as output after we have written our label description and we have used them with our zero-shot model. So we would have n items, and then for each column we would have a set of predictions from a different zero-shot model with different label descriptions. And this is what goes in input to our IRT model. So in our case, we use the maze model from Hovi et al. I'll briefly explain how it works. We have I items and n annotations. Here on the left, we see the input to this model. And here on the right is the model plate. So y, e, n, basically like the value 1, is the only observed variable that we have here. And then we're going to say that the value of this variable is going to be dependent on some latent unobserved gold truth. For instance, if we had our text, I missed my flight, then it would be class negative, and we don't observe this. So, and this is what determines in part this label. And then we're going to say that this label is also determined by the behavior of the model or the annotator, let's say the worker. And what we want to do is to model this behavior. And we have J annotators, which in our case corresponds to N. And we're going to put a parameter on the behavior of our model, a theta parameter, that will model the credibility or the reliability of this model or annotator. And we're going to say that high values of this parameter, so if a model is highly credible or reliable, ideally would correlate with our performance metric like accuracy or F1. And finally, we can say that a specific annotations is also dependent on the behavior of a model on a specific instance. And we model that with parameter epsilon. We train this model using MCMC. And here is our proposal when we put everything together for having a zero-shot classification pipeline that can estimate the reliability of itself or of its label description. So we have some input text here on the left that we want to classify. We have a set of different label descriptions. In green, you see the one for class positive. In red, you see the one for class negative. We embed the text and all these label descriptions in the same semantic space. And then if we have n label descriptions, we will have n predictions, as you've seen before. This goes in input to our probabilistic model, which will give us two things: an estimate of the reliability of each label description and an inferred gold truth. at this point, we need some source of variation regarding the label descriptions. So as I said, we don't know how to best frame a label description. So we try to write several of them and see what works best. So if we have two classes, negative and positive, we can start with the identity label description with the word of the class itself, like the word negative for the class negative. We can then have some variations on this word by taking some synonyms like the word bad or great instead of the word negative or positive. And finally, we introduce a third source of variation, which is pattern variation. These patterns are clause style phrases that take these label description words, then turn them into real sentence, hopefully to help the sentence transformer models work a bit better. So like we have the empty or the empty pattern that consists of the word itself. We can have something like the movie was just something. Here's an example for the IMDb movie review dataset of the kind of variations that we have. We manually write some synonyms, and then we experiment with machine translation. Since we use multilingual embedding model, it means we can provide labels in Spanish or Portuguese, even if the text is in English. And then we manually write some different patterns. Okay, so first thing we do, we look at ranking correlations between our theta parameter of our maze model here in the first column and the true F1 computed using the available labels, since we have labels for all these data sets. And the idea here, as I said, is if we have high values of theta, we would like to have high values of F1. And you can see that in some cases we do a really good job in this case. Here on the right, you see a baseline that does the same thing, but using the kappa interannotator agreement metric computed between all the label description. And here's the correlation with the F1. And on average, using a model outperforms the baseline by quite a bit. And then second thing we could do is to use these aggregated labels that this model provide, or even do majority voting as a baseline. So here you see macro averaged F1 for all the data sets. Here on the very left, you see what happens when we use only the identity label description as a baseline, more or less just the class name of each class. And then here in the first column, it's what happens when we play with the manually written label description. So when we use maze, we usually can improve on the baseline performance. By varying the pattern and keeping the label description fixed, we can do a bit better. And interestingly, we get the best results when we use machine translation to create variation for our label description. And this is nice because it means that in theory, we can write label description once, use machine translation to generate several variation of this, and then use either majority voting or a probabilistic model to infer the best label. And this leads us to better results. So to conclude, if you have a zero-shot model and you need to write a label description for using it, you can write several of them and then use a model to find the best one. And translation can help you in this if you have a multilingual embedding model. And if you want to infer the best label, you can use the same probabilistic model to do that. And that concludes my talk. Thank you.
Thank you, Angelo. Does anybody have any question for Angelo?
I would like to ask if you already have like the pattern and you generate the labels, why don't you just use the data you generate to train normal classificator? And I would say that it can perform better than this one.
So you mean to?
I mean, you in the previous slide you have like the pattern, and you just like this one. Yeah, there's a pattern. You can just generate the data. It was positive. It was great. It was really great. And based on that, you can train the text classificator, for example, neural network or logistic regression for the class positive and negative, because you are still distinguishing only between these two words.
But to do that, you would still need to know that, for instance, the pattern "it was awful" is a good label description for the text, like I missed my flight, say, right?
Yeah, but you need to know that anyway, right? If you
not really. So what we do, we write these descriptions, and then what happens that we are in this space. So we wrote the text, this person feels sad, and the text, this person feels happy, right? And until we compute these distances, we don't know if this text, this person feels happy, is a good close neighbor of the text I missed my flight, right?
Yeah,
so
but
what you say,
sorry,
please go ahead.
I was just saying that then you don't want to like compare the similarities like distance, but you train the normal like text classification and you do softmax because you know that you have like the two classes.
I think what you're saying can be done as maybe as an additional step, as a form of distillation, and it has been done before in the literature. There is this PET paper from Schick and Schütze, and they do something like that. So they write several of these descriptions, and then they have a distillation process. This approach is a post-deployment solution, doesn't need access to the model, only to the prediction. So it's a bit faster, but yeah, to some extent, like you could do something like that. Probably you could combine it to maybe like increase the performance. But like you would still need to compute this metrics at some point if you're using this sentence similarity model.
Okay, thank you.
Yes. We have another question.
Yeah, thanks for the very interesting talk. I think this is like one of big problems to come up with actually good label names. So I was wondering during the talk, now that you have like methodology to come up with better label names, you also mentioned like the kappa score. Do you plan to evaluate how coming up with better label names and label description will maybe improve inter-annotator agreements like on the same data set if it's being labeled again? And if you also see the same effects for like data sets that have like in the region of 20 or more label classes.
Thanks for the question. Yeah, there is some work already on trying to automatically generate some label descriptions. Translation is usually a good option if you want to guess, but there are some more principled approaches but require actions to the access to the model weights. And regarding the second questions, we had some issues with some data sets with several classes. And when we ran our experiments, we used the cosine similarity as scoring functions. We reran them with a dot product instead of cosine similarity, and that seemed to fix the issues for the data sets with several labels. So hopefully that would be a good solution.
Okay, thanks. I don't know if we have more questions. Hi, Angelo, Paolo speaking. With respect to the slide you are sharing, I just wanted to let you know that you are not the only one to have missed your flight. And so there is another person that feels sad, and actually another Italian, Davide Buscaldi. So of course, we know that it's a little bit too much to speculate and to pretend to find a common patterns from two samples, but at least it seems that Italians trying to fly to Valencia have some problems. Okay, Thanks, everybody. And please, Davide, pay attention not to miss the flyback because it would be too much. Bye-bye. Bye, Angelo. Grazie. Ciao.
Bye-bye. Thank you.
Thank you, everybody. With this, we finalized the industry track today. Thank you for attending it and for participating. And now Viviana is going to be the chair of the next